Have you ever just stopped and thought about the absolute magic that's packed inside your phone? I mean, really thought about it? Or the device you're watching this on right now? It's a whole universe of information, a creative studio, a portal to the entire world, and it's all powered by a tiny little sliver of silicon. So the big question is, how on earth did we cram so much power into such a tiny space? Well, the answer isn't just one single invention. It's a relentless 50-year-long shrinking act that literally bent the future. So let's dive into the law that made it all happen. Okay, just look at this contrast. On the left, that's the ENIAC from 1946. It was the first general-purpose electronic computer, and it was a monster. We're talking 30 tons filling a room the size of a small house. And on the right, that's a modern microprocessor you can balance on your fingertip. The journey from that behemoth to this little powerhouse is honestly one of the greatest stories in all of technology. So how did we get from there to here? Well, it turns out this incredible shrinking act, it wasn't an accident. Not at all. For over half a century, it followed a shockingly predictable pattern. And here's the wild part. It wasn't a law of physics. It was just an observation. An observation that became a kind of self-fulfilling prophecy for an entire industry, pushing human ingenuity to its absolute limit. And this is it. This is the observation at the heart of everything, Moore's Law. It's a simple but profoundly powerful idea. The number of tiny switches, transistors, that we can cram onto a chip doubles about every 2 years. Now think about that for a second. That's not just adding more power, it's exponentially more power, more speed, more capability, all while getting cheaper and cheaper. It basically became the drumbeat that the entire tech industry marched to. And this quote right here takes us back to the very beginning, 1965. A guy named Gordon Moore, who would later co-found Intel, was just noticing a trend. He saw that the number of components on a chip had been doubling every single year, and he made what he called a wild extrapolation, just a guess. He later tweaked it to every 2 years, but that single observation set a relentless pace for decades of innovation to come. Now, to really, really appreciate this electronic revolution, we've got to rewind the clock way back. Because before silicon and circuits, the whole idea of computing was a physical, mechanical thing. A world of really intricate gears, spinning levers, and even steam power. Our journey to compute starts way before electricity was even a thing. As you can see, it goes all the way back to the abacus around 500 BC. Fast forward about 2,000 years, and you get Blaise Pascal building a mechanical calculator to help his dad with taxes, which, let's be honest, is a problem we're still trying to solve. But the real visionary here, the person who was way ahead of his time, was Charles Babbage. His designs from the 1800s were basically the blueprints for the modern computer. Babbage's analytical engine, which he designed in 1833, was the blueprint. It had a processor, he called it the mill, and it had memory, which he called the store. It was even programmed using punched cards. I mean, it's just an incredible piece of foresight. And working right there with him was Ada Lovelace. She saw the potential beyond just number crunching. She wrote what we now consider the world's very first computer program, an algorithm for the engine to compute something called Bernoulli numbers. The mechanical era was absolutely brilliant, but it was limited. The real leap forward, the one that changes everything, required a whole new medium, a new way to control the flow of information. So let's jump into the electronic age and see how this all built, starting with a technology that was big, hot, and, well, notoriously flaky. And we're back to the ENIAC. This was a first-generation computer, and its brain was made of nearly 18,000 vacuum tubes. These big glass tubes acted like light switches, but they were huge, they ate up enormous amounts of power, they generated incredible heat, and they were constantly burning out. Seriously, the ENIAC was often down for repairs more than it was actually running. It was a monumental achievement for sure, but a practical dead end. Then came the breakthrough. It came from Bell Labs in 1948, the transistor. It did the exact same job as a vacuum tube, acting as a switch or an amplifier, but it was made of solid silicon, had no moving parts, and was just better in every single way. It was tiny, it barely used any power, it ran cool, and it was incredibly reliable. This was the invention that made everything else possible.
And the next breakthrough was right on its heels, the integrated circuit, or IC, in the late 1950s. Instead of wiring up all these individual transistors by hand, engineers figured out how to manufacture dozens of them, plus other little components, all at once on a single monolithic piece of silicon. And just like that, computers could get smaller, faster, and much, much cheaper to build.
The invention of the integrated circuit is what lit the fuse for Moore's law. With a way to mass-produce transistors on a single chip, the race was on. The goal was simple: make the transistors smaller so you can fit more of them in the same space, and then do it again and again and again. And the pace of progress was just breathtaking. These acronyms you see, LSI, VLSI, they represent these huge leaps in complexity. We went from thousands of transistors on a chip to tens of thousands, and then hundreds of thousands. And each step up this ladder brought us closer to the ultimate prize: cramming an entire computer brain, the central processing unit, onto one single piece of silicon. This was the birth of the microprocessor. And this is it, the Intel 4004 from 1971, the first microprocessor ever sold to the public. It seems so primitive now, but this one little chip had all the logic that, just a few years earlier, would have taken up a whole cabinet full of electronics. This was the seed from which the entire personal computer revolution would grow. To really get a handle on the sheer power of this exponential growth, just think about this. In 1997, for the 50th anniversary of the ENIAC, a group of university students recreated its entire functionality on a single chip of silicon. 50 years of Moore's law took a 30-ton room-sized machine and shrunk it down to something smaller than your fingernail. That's just mind-blowing. And today, well, the scale is just staggering. A high-end graphics processor in 2025 can have over 92 trillion transistors. To put that into perspective, that's more transistors on a single chip than there are people on planet Earth. And every single one of them is a microscopic switch firing trillions of times per second. That is the incredible legacy of Moore's law. And this incredible explosion in power and the massive drop in cost is why these machines exist. The microprocessor made the personal computer possible. It took computing out of these giant air-conditioned labs and put it on our desks with machines like the Apple II in '77 and the IBM PC in '81. But, all exponential curves eventually face a reckoning. For decades, we rode this incredible wave of progress, but now the industry is facing a really fundamental question. After more than 50 years, is the free ride finally over? You see, since around 2010 or so, that reliable 2-year doubling has started to slow down. We're literally starting to run up against the fundamental limits of physics. Transistors are now so unbelievably small, we're talking just a few dozen atoms across, that electrons start doing weird quantum things, like leaking out of the channels where they're supposed to be. And this physical wall has sparked a huge debate. On one side, you have people like NVIDIA CEO Jensen Huang, who in 2022 just put it bluntly: Moore's law is dead. For him, the economic reality is clear. It's just become way too difficult and expensive to get the same performance boosts just by shrinking transistors anymore. But then, just days later, the CEO of Intel, Pat Gelsinger, shot right back, saying the law is alive and well. And his argument? He says the spirit of Moore's law isn't just about shrinking things. It's about finding clever new ways to keep packing more and more computing power into our devices. And this is the core of what people are calling the more than more philosophy. The new strategy is all about clever engineering. If you can't shrink the components anymore, you find new ways to arrange them. Think of it like a city. If you run out of land to build out, you build up. You build skyscrapers. That's what engineers are doing with 3D chip stacking. They're also redesigning the transistors themselves and exploring all sorts of exotic new materials. The key takeaway is this: the old, easy path of just shrinking everything, that's gone. But human ingenuity, that hasn't stopped. Progress has just changed direction. And so that leaves us with this really fascinating question for the future. For half a century, Moore's law was this predictable, reliable engine that drove our digital world forward. Now that that engine is starting to sputter, the race is on to find the next one. What new discovery, what big idea is going to define the next 50 years of progress?